Okay, so last time we started section 2.1 over mathematical systems, direct proofs, and counter examples. We talked about the first two of these topics last time. We didn't quite get to counter examples. And what we're going to do today is another example of a direct proof using a different mathematical system. And then we'll talk about how to use counter examples to show that theorems are actually false. So they're not really theorems at all. Okay, so for a little bit of review, a mathematical system is simply a collection of axioms, definitions, and probably some undefined terms. And you actually know lots of examples of these, even if you wouldn't have known to call it a mathematical example, mathematical system. One of the examples that we talked about last time was geometry, Euclidean geometry. So that's what you learned in high school and what you would talk about in most geometry classes. We also discussed a little bit about the mathematical system of real numbers. This has axioms like multiplication is commutative, or there is a number 0 that you can add to any other number and get the same thing back. Okay. And this is just a small collection of the axioms. There are a lot more if we wanted to go into detail. And then there are all sorts of definitions, like what is a triangle in geometry, or what is a positive number for real numbers. And then theorems are things that you can prove are true using logic and then your axioms, definitions, and undefined terms. And examples of these are like this one about equilateral triangles. This one says if a triangle is equilateral, then its angles are also equal. Or you can have something from the real numbers, like this one, that says that for all real numbers x, x times 0 is equal to 0. So that's something that you can prove using your axioms. And then the kind of logic that we learned in the previous chapter. So to connect your ideas together, you would have to use logic. Okay. So that's kind of the idea of what we're doing. And then we talked about more of the nuts and bolts about proving things. We talked about how to prove an if-then statement directly. Let's just talk about the conclusion of this. For a direct proof, you would only have to consider the case where the hypothesis is true, the if part is true, because if the if part is false, then the overall conditional statement is vacuously true. So in our direct proof for a conditional statement, we only had to assume that the hypothesis was true and then prove using logic and other axioms or definitions that the conclusion was true. Then maybe we should talk about the actual example of a proof that we did for even and odd numbers. And the concrete mathematical definition of an even number looks like this. An integer n is even if there exists another integer k such that n equals 2 times k. And the odd definition looks like this. An integer is odd if there exists an integer k such that n is equal to 2k plus 1. And this is how it works out. This is the precise mathematical definition, and here are some examples of how that actually works. So for even numbers, you're both looking at 2 times things to get even numbers. For odd numbers, you're looking at an even number, basically, and then you're putting an extra 1 on it to get an odd number. Okay. And then we actually constructed our proof I don't want to go over the proof that we wrote too much. What I want to focus on is the format of writing a proof, because we're going to write another proof in just a second. So the general format was you want to write something like the word proof to let the reader know that you're about to prove something. And then you need to write your assumptions, what you're trying to prove, and then using logic, you'll work through definitions to connect your assumptions to your conclusion, what you're needing to show. And then at the very end, you'll want to write your conclusion. And I left off one bullet point down here. Usually in math, when you're proving something, there's a symbol that you'll use to show that you're done with your proof. So your proof starts with a word like that, and it ends with another symbol. And I'm going to use this one. It's just a square, an empty square, to tell the reader you're done. You could also fill in your square to represent that you're done with your proof. And in your textbook, they use a different symbol. They use a triangle because they use squares as bullet points. So they use something different for their end of proof symbol. Okay, so that's where we left off last time. I guess before I change the page, are there any questions over what we did last time, over making a proof? Okay, so Davian's asking to see it again. And yeah, we're going to do another example of a slightly different kind of proof. So that we can see how these work again. Okay, so this is the next, excuse that noise. This is the next thing that we're going to prove. And this is about sets this time. So we're going to be using the ideas that we learned in way back at the beginning of class from section 1.1 to try to show that this is true. This says for all sets X, Y, and Z, this equality is true. And this is the intersection of X and Y minus Z on the left side. And this is the intersection of X and Y minus the intersection of X and Z on the right-hand side. So there's a few things we need to discuss before we get to the nuts and bolts of our proof. The first thing to do is to recognize the form of this proposition. So this is a universal or universally quantified, but there's actually 3 variables. So that means there are actually 3 universal quantifiers. Oops. I can make that look a little better. And then we have some propositional function. In this case, it's an equation. We'll just call it P of x, y, and z. So we have three quantifiers nested. And instead of a conditional proposition, like we had last time, we have just an equation. So this is an equation. And in order to show that this is true, we have to show that the equation works no matter what sets we actually plug in. So let's write that out. To prove the proposition, we must show that the equation, and we can just write it out again. So it's x intersected with y minus z on the left side, and that should be equal to x intersect y minus x intersect z. We must show that this is true no matter which sets we actually plug in. And that means we also need to think back to what it means for two sets to be equal. So if we're looking at something like the set A is equal to the set B, then you have to show that all of the elements of A are elements of B. And you also have to show that all the elements of B are elements of A. Okay, so now that we've thought through some of these things, some of these ideas that we already know, we can try to format our proof. So we know that we're going to need to start with any sets x, y, and z, and then we're going to have to show that the elements of the left side are also elements of the right side. And then we'll have to show that all the elements of the right side are also elements of the left side. And then once we've shown both of those things, we can conclude that the two sets are equal. So let's go a little bit further down and write the word proof. Since we're going to start proving something now. I'm going to break my page into two columns so that I can write some notes over here on the right in case we need to. So we need to start by writing proof like we already did, and then we need to write our assumptions. In this case, we're just assuming that x, y, and z are sets. And now we need to tell the reader what we're trying to conclude, what we need to show in our proof. Okay, and this is what we're going to do in order to show that the equation is true, that x intersect y minus z is equal to x intersect y minus x intersect z, we need to show two other things that we already talked about. We need to show that elements of this side are in the right side. So if x is an element of x intersect y minus z, then x is an element of the right side. X intersect y minus x intersect z. Not quite done. And if we have an element of the right side, maybe we'll give it a different name, lowercase y. So it'll be an x intersect y minus x intersect z. Then we need to show that it's in the left side. So y is an element of x intersect y minus z. So we just wrote what we need to show. And then after that, we need to do it. We need to actually go through the logic of showing, using the assumptions that these two parts are true. So use logic to connect your assumptions to your conclusion. Okay, so what I would do if I was writing this proof is I would probably start a new paragraph and start with this. So if x is an element of the left side, or maybe suppose x is an element of the left side. So x is in x intersect y minus z. Then we have to remember what an intersection means. If x is in an intersection, that means it's in both this set and that set. So then x is an element of capital X, and x is an element of y minus z. Then we have to remember what set subtraction means. So this set, y minus z, is the set of elements of y that are not in z. So we can just write that out, or what it means for x. So since x is an element of y minus c, we know that x is in y, and it's not an element of z. Okay. So we're just working through definitions. We know at this point that x is in capital X is in y, and x is not in z. So we know three things about x. Let's see if they add up to meaning that it's an element of the right side. X intersect y minus x intersect z. What do you think? Well, we know it's in both, we know x is in both x and y. That means little x is in the intersection of the two sets. And since we know little x is in capital X, but it's not in the set Z, then it's not in the intersection of the two sets. Oops. And this should be Y, of course. So X is not in the intersection of capital X and Z. And then we can conclude that since X is in the intersection of X and Y, and X is not in the intersection of X and Z, then it is in the right side. X is an element of capital X intersect Y minus capital X intersect Z. Okay, so that's half of the proof. We've shown that if little x is in the left-hand side, then it's in the right-hand side. Now we need to do the other part. Let's start with an element y in the right-hand side and show that it's an element of the left-hand side. So we'll need to go to some blank space and continue working. So we're going to suppose that y is an element of x intersect y minus x intersect z. That means y is an element of this intersection and not an element of this intersection. From this first part, we know that y has to be in both of the sets. both of the sets x and y. So y is an element of the set x, and y is an element of the set y. But since it's not in the intersection of x and z, we know that of these two sets, there has to be one where y is not an element. So y is an element of x. So if it's not going to be in this intersection, that means it can't be an element of z. Okay. So now we know three things. Y is an element of x, y is an element of the set y, and y is not an element of the set z. And now we need to connect it back to the left-hand side of our original equation. So x intersect y minus z. We already know that it's in x. We just have to conclude, or we also have to show that it's not in, flip back. It's not in y minus z. So since, now we're talking about the element y, since it is an element of y, and little y is not an element of set z, we know that y is not, y is an element of y minus z. Like this. So we have two facts that we can put together. Y is an element of x. Y is an element of y minus z, set y minus z. So it must be in the intersection. Of x and the set y minus z. And now we're done. We've done what we set out to do. We showed these two things. So we just need a concluding sentence. Something like, in conclusion. Oops. That's bad handwriting. In conclusion, we can say the two sets are equal. X intersect y minus z is equal to x intersect y minus x intersect z. And then we can put our little box to show that we're done. So unfortunately, we don't have a lot of time to discuss the proof, but you can come back and look at it. And your textbook also has some discussion over this particular example. We need to get straight to the counter example, since you're going to have things like this on your homework as well. So a counter example is what we're going to use to disprove, to show that a universally quantified statement is false. So in order to show that this is false for all x, p of x is false, we need to find at least one value of x where the propositional function is false. And this value of x that we find is what we call a counter example. So we find something where the proof is false. So let's use that on this relatively simple statement that says for all n in the positive integers, 2n plus 1 is prime. So what we're trying to do is find a natural, well, let me use the same word, find a positive integer n where this is false. So 2 to the n power plus 1 is not prime. We only have to find a single example. We don't have to worry about all numbers. A single example where this is false will show that the universally quantified statement is false. So let's just plug in values. Just start at 1 and see what happens. So 2 to the 1 power plus, 2 to the 1 power plus 1. That's 2 plus 1 is 3. That didn't work. 3 is prime. What about n equals 2? 2 squared plus 1. 4 plus 1 gives us 5. Well, that doesn't work either. Oops. What about n equals 3? 2 to the third power plus 1. 2 to the third power is 8, plus 1 is equal to 9. So there's our counterexample, because 9 is not prime.